Okay, I'm going to just work one problem here out of 12.4 because the homework assignment, I believe, is just going to be one problem. I'm going to work number 12. It says find the center of mass of the lamina in exercise 11, and then it talks about the density function. So first of all, the lamina in problem 11 is this disk in the first quadrant, which means it's kind of like the unit circle here, but everything inside of it, right, only in the first quadrant. And it tells me in number 12 that the density at any point is proportional to the square of its distance from the origin. What that means is that if I pick any point inside this lamina, the density, well, I'll put it up here, the density at that point xy is proportional, so a multiple of the square of the distance from that point to the origin. So if I look at the distance from here to here, remembering that this is the point xy, by the Pythagorean I can set up a right triangle. I know that this length is square root of x squared plus y squared. That's the distance from the point to the origin. And the problem says the density function is proportional to the square of the distance. So I square that and I get x squared plus y squared. So that is our density function. We're trying to find the center of mass of that lamina. So let's now talk about the mass. The mass of a lamina should be the double integral over the region D of the density function with respect to area. So I need to somehow determine what kind of region I'm looking at. That looks like a really good polar region. If I let theta go between 0 and pi over 2, and I let r range from 0 to 1, I should draw that region, which means my mass integral is going to get converted to a polar integral, which means it's going to become r d theta. And I'm going to integrate the density function, but switched over to polar. So when I switch this to polar, x squared plus y squared, remember, is r squared. So this is just going to become k r squared. I'll put the k on the outside, r squared. And my limits of integration are 0 to pi over 2 and 0 to 1. So that's the double integral I need to do to find the mass of that lamina. Then I'll go on and find the center of mass. So this is r cubed. So I'm going to go ahead and start integrating. 0 to pi over 2. Antiderivative of r cubed is 1/4 r to the 4th. Evaluate from r equals 0 to 1. And then I'll integrate with respect to theta. So if I plug in 1, I get 1/4. If I plug in 0, I get 0. So this is going to become k times the integral 0 to pi over 2 of 1/4 d theta, which is just take the antiderivative, k times 1/4 theta evaluated from 0 to pi over 2. When I plug in pi over 2 here, I'm going to get k times 1/4 times pi over 2. That gives me k times pi all over 8. And then when I plug in 0, I get 0. So I should have k pi over 8 will be my mass. So if someone tells me what the proportionality constant is, then I will be able to tell them the mass of this lamina. Now the next step is to find the x bar. So I'm going to go after the center of mass now. I have to find x bar and y bar. X bar, okay, x bar is going to be the moment about y over the mass, which is the same as 1 over the mass times the moment about y. And I gave you this in your notes. That's going to be x times, well, the double integral over d of x times the density function with respect to area. So this becomes, well, 1 over the mass is the reciprocal of the mass. There's the mass, so it becomes 8 over k pi. Double integral. Now I already know what happens if the x isn't there, right? I get this. I convert to polar, but now I have an x there, so I have to take that into account. I'm still going to go to polar, so it's still 0 to pi over 2, still 0 to 1, but my x needs to be replaced with my polar conversion. And remember, x is r cosine theta. So I'm going to have r cosine theta, that's x, times the density function, which was k times, remember, x squared plus y squared, but we said that's r squared. Then the r d theta from the fact that we are converting to polar. So x, density function, r d theta. Let me clean this up. This k is a constant, can come out of the double integral and cancel with that k. So we get 8 over pi, integral from 0 to pi over 2, and then integral from 0 to 1 of, let's see, we have cosine theta, we have r to the 4th. So I'm going to put r to the 4th cosine theta, dr d theta. All right. Hold on, I'm just looking at something real quick. Yeah. Okay. Integrate the inside one with respect to r. So we're going to get 1/5 r to the 5th cosine theta evaluated from r equals 0 to 1. And then I'll integrate with respect to theta afterward. If I plug in 1, I get 1/5 cosine theta. If I plug in 0 for r, I get nothing. So this just becomes 8 over pi integral 0 to pi over 2 of 1/5 cosine theta d theta. And that should be easy enough to integrate. So 8 over pi, no more integral, so antiderivative of 1/5 cosine theta is 1/5 sine theta. And I'm evaluating this from theta equals 0 to theta equals pi over 2. All right, so plug in pi over 2 for theta, you get sine of pi over 2, which is 1. So if I plug in 1 here, I get 1 right here for sine theta. I just get 8 over 5 pi. And if I plug in 0, sine of 0 is 0, so everything goes away. So I should get 8 over 5 pi. This is x bar. So how do I want to put this? I'll put x bar right here. Remember, the center of mass of this thing, the center of mass is some point x bar, y bar. And what I've determined so far is that the x coordinate is 8 over 5 pi. And now I'm going to see about the y coordinate. So to do y coordinate, y bar, this changes to the moment about x, right, which changes this to y. And then I come in, I do the same thing. 1 over mass is still this, integral is still the same, but instead of x, density function, and then the polar conversion, I'm actually going to have y here. And y converted to polar is r sine theta. And that changes this right here to r to the 4th sine theta. Nothing changes in all this. This is sine. Right here, this is sine. And then coming over here, now here's where we get a change. Antiderivative of sine is negative cosine. So this is going to become negative cosine. I'll just put the negative out here. Negative cosine of theta. Okay, so how does that change our answer? If we plug in pi over 2, cosine of pi over 2 is 0, so we just get a 0 for the first one. The second one, we plug in 0. Cosine of 0 is going to be 1, so we get all of this. We get negative 8 over 5 pi, and then minus a negative is plus. So we actually have a symmetric, which kind of makes sense, that our lamina is symmetric. Because if we look at this, we're going from the origin. As we pick points and go out, our density changes, but the change that we have is proportional to how far away we are. So our center of mass should have the same x and y coordinate. For this particular problem, it's not always that way. So you would figure out where those were. Let me figure out what 8 over 5 pi is, just so you have an idea as a decimal of where that is. Clear. 8 over 0.509. 0.509, 0.509. So not quite halfway, a little bit more. Here's 0.5, a little bit more than that up. Here's 0.5, a little bit further up. So somewhere in there, that's your center of mass. Okay, I'm now going to do number 18, which asks you to calculate the moment of inertia about x, the moment of inertia about y, and the moment of inertia about the origin for the problem we just did for number 12. So if you go and you look in your notes, the definition of this double integral over d of y squared times the density function with respect to area. This one is the double integral over d of x squared times the density function with respect to area. And this one is just those two answers added up. So let's take a look at this first one. We're working, remember, with the problem that we just did. So remember that when we converted this to a double integral in polar, it went 0 to pi over 2, 0 to 1. But now we have y squared. And remember, y in polar is r sine theta. So it's r squared sine squared theta. Then the density function, which was k times r squared. Then, because we're in polar, r d theta. And so what I'll do is I'll pull the k out completely. Integral 0 to pi over 2. Integral 0 to 1. I should have r to the 5th here, sine squared theta dr d theta. The antiderivative of this with respect to r is going to be 1/6 r to the 6th sine squared theta d theta after we... Robert. That's the antiderivative. I need to evaluate it from r equals 0 to 1, and then d theta. When we plug in 1 for r, we get 1/6 sine squared theta. We plug in 0, it's all gone. So this is just going to become k integral 0 to pi over 2 of 1/6 times sine squared theta d theta. And to integrate that, we go back to Cal 2 or pre-Cal. Remember the identity. Sine squared theta equals 1/2 minus 1/2 cosine 2 theta. That was called the power reducing or half angle identity. We also had another one that looked like this, 1/2 plus. So remember that from Cal 2. So that's what I'm going to do here. And I think I'll actually pull the 1/2 out of this, make it 1 minus cosine 2 theta. So pull the 1/2 out of both. And let me rewrite this line. That line will become, let's see, the 1/6 I'm going to pull out with the k, and the 1/2 I'm going to pull out. So I'm going to get k times 1/6 times 1/2, which is k over 12, integral from 0 to pi over 2 of 1 minus cosine 2 theta d theta. And at that point, I just integrate. So k over 12 times the antiderivative of that, which is antiderivative of 1 with respect to theta is theta, then minus 1/2 sine 2 theta is the antiderivative of this, evaluating from theta equals 0 to pi over 2. So if I let pi over 2 go in for theta, it becomes pi over 2 here. Sine of, let's see, 2 times pi over 2 is going to be pi, sine of pi is 0, so it zeroes out. So I just get k over 12 times a pi over 2. And then minus, now what happens when I plug in 0? 0, sine of 0 is 0, so we just get 0 for the whole thing. So we get k pi over 24. Now, I'll let you do this one on your own, this right here, but when you do the x squared, instead of having r sine theta squared, you're now going to square r cosine theta. And what happens in that, let me write it, I'll just write it down. It'll become integral 0 to pi over 2, 0 to 1. This right here will be r squared cosine squared theta. You'll have your density function. You'll have r d theta. So that's the only difference. And then the k comes out, and your integration of r is still the same, but you'll have to integrate cosine squared when you get past the r integration. And so you use this formula instead of this one, which changes this to a plus. That's the only difference. And then that's a plus. And it does not have any impact on the answer here. And so you should get, for both of these moments, okay, this one should be k pi over 24, and this one should also be k pi over 24. And so when you add those two up, which is this answer, you get k pi over 12. Now this is just one example. I mean, these problems can get kind of messy because it doesn't always have to be a polar region. It can be a type 1 region, type 2 region. You just have to be careful with all the little integration pieces on the inside. Okay, that's it.